Alright, so today we're going to do a little bit of kind of some example problems where you have to explain why something is the way that it is, and talk about linearization with an example problem, okay? So, first of all, let's talk about finding information about a graph using the area under the curve. So, here I have a graph of velocity versus time, okay? So that means the slope of my graph is acceleration, which is good, but what I want to know is what's the total displacement. The total displacement is literally the area under the graph, the area that's covered by the graph. So, so here, you have on this side, you have, this is velocity, and this is time. And if you notice, this is a rectangle. Well, how do you find the area of a rectangle? It's just, like length times width, right? Well, the length is velocity. In this case, it's your V0, because that's what's right there. So, because the distance from here to here is your V0. So, V0 times the time, right? That's the area for that rectangle. And then this is a triangle. So now we've accounted for this area with just saying V0 times T. So now we have to account for this area. Well, plus this area. So that's a triangle. A triangle area is just 1/2 base times height, right? So, so we would do 1/2 in your base, right? This is your time, and your height is your velocity, but it's from here to here, so it's this. Your V. But technically, from here to here, this is your change in velocity. So it'd be my change in velocity times time. And that would give me the area of both of those, which would be my total displacement. Okay? Okay, so now let's apply kind of that concept to this next problem. So this next problem, so I have a curve, and this is velocity versus time. Sorry, the graphic is a little messed up, but you can still see that this is time, okay? So it says the graph above shows velocity versus time for an object moving in a straight line. At what time, after t equals 0, does the object again pass through its initial position? Okay, so if I want to know the displacement, right, I need to figure out the area. So first I need the area of this part. Well, that's a triangle, right? So that part is going to be 1/2 base, which is +1, times height, which is -1. Well, that's 1/2 times -1, which is -0.5 meters. Okay. So from 0 to 1 seconds, it's at -5 meters. So in order for it to go back to its original position that it was at 0, I have to go at least another 1/2 meter, but in the positive direction. So I'm going to look at what's the area under this triangle right here. Okay, so the area under that triangle, so it's 1/2 base, which again is 1, but the height this time is going up to 2, so that's 2, and that's positive. So 1/2 times 2 is just 1 meter. So, and I don't really have enough data to tell me exactly where this is going to be, but I'm going to say it's probably between 1 and 2 seconds. Okay, so because it is accelerating, so I can't tell for sure, because it's not at 1 second, and I don't have a choice for 1.5-ish, so I'm going to say it's between 1 and 2 seconds, and that's why. Okay, the area under the curve initially it goes 0.5 meters in a negative direction, I needed to go 0.5 meters in a positive direction to get back to where it started from. Okay, so all right, so that's how we use that displacement under the curve graph. All right, so question 2. Okay, this one I have displacement versus time. So displacement is displacement of x of an object moving along the x-axis. So that means it's just going straight horizontally, not the x-axis of this graph. Is shown above as a function of time. That's why time is on the x-axis. The acceleration of this object must be, well, so what's happening here, I can kind of draw out the other two graphs based off of this. So this is your slope here. Your slope is a positive number and it doesn't change. There's no curve. So that means my velocity versus time graph is just going to be the slope of this graph. So it's going to be a straight line in a positive direction, which means it's moving at constant velocity. So if it's moving at constant velocity, it's not accelerating. So acceleration of the object must be 0. And that's it. Okay? All right. So let's look at doing a little math and then a little graph at the end. Okay? So here's a little old free response question. So we have a race, right? And we have a 100-meter dash race. It says the first meters of a 100-meter dash are covered in 2 seconds by a sprinter who starts from rest and accelerates with a constant acceleration. The remaining 90 meters are run with the same velocity the sprinter had after 2 seconds. So my first meters that are covered in 2 seconds, it's the first 10 meters that's covered in those 2 seconds. Okay, so the first thing you do, determine the sprinter's constant acceleration during the first 2 seconds. So sometimes it helps to kind of line up your variables in the left-hand margin, see what you have. So if something is accelerating, it has a v-naught, a final velocity, an acceleration, a displacement, and a time. So I kind of just start by figuring out what are all of these. So if it starts from rest, my initial is 0. I don't know my final or my acceleration, but my displacement covered in the first 2 seconds is 10 meters. So first I want to find the acceleration. Okay, well, I can use the displacement equation for this because I've got displacement, my initial velocity is 0, I'm looking for acceleration, and I have time. So I can say my delta x equals v naught t plus at squared over 2, or 1/2 at squared, but again, I just don't really like fractions. So my v naught t is going to go away because my initial velocity is 0. So then my delta x just simply equals at squared over 2. So I need to get my a all by itself. I'm going to multiply both sides by 2, divide both sides by t squared. And so my acceleration equals 2 times 10 over 2 squared. So 2 times 10 is 20 divided by 4 is 5 meters per second squared. So that's my acceleration for the first 2 seconds. Then I want to know what's the velocity after those 2 seconds have elapsed. So now I'm looking for the final velocity. Okay? Well, there's a few different equations you can use for this. I feel like the acceleration equation is pretty easy. So I would say a is v final minus v initial over time. And my v initial is 0. And I just need to multiply time on both sides. And I have final velocity. So 2 times 5, and I get 10 meters per second. So then the remaining 90 meters are run with 10 meters per second. Okay, so now I need to know the total time needed to run the full 100 meters. So I need to figure out, so I know the first 10 meters was run in 2 seconds, so now I need to figure out how long did it take to run the last 90. I'm going to use my v-average equation. My average velocity is displacement over time. Okay, well, I'm looking for time, so I just rearrange this. So time is just displacement over average velocity. So 90 over 10, which is 9 seconds. But I add an additional 2 seconds for the beginning, so the total time is 11 seconds. Okay? Alright, so then it says, on the axes provided below, draw the displacement versus time curve for the sprinter. Well, I know that after 2 seconds, he's gone 10 meters. So at 10 meters, 10 meters in 2 seconds, I'm hitting a constant velocity, and I know that at 11 seconds, I will have gone 100 meters. So I'm going to kind of start with that, and I'm going to draw a straight line with my little ruler that's really dinky and silly. Okay, so I know that that's moving at a constant velocity, which means it's going to be a straight line. And then from 0 to 2, it's going to be a little bit of a curve. So, and it's really hard to draw a curve that's kind of that small, but that's basically what it would look like. So this is your graph of displacement versus time. Okay? All right. Moving on. Okay. All right, so let's talk about graph linearization. So here's an example. So I have, what I have is as time goes by, my distance is increasing more and more and more, but not at the same rate. Look, see, this is going up, okay, and this is going up more than this interval, and this is more than this interval. So that means that this is accelerating, okay? If at each time interval of 2 seconds, if we were going up the same amount, you know, between here and here, between here and here, between here and here, I would know that I'm not accelerating, but this is accelerating. So since it's accelerating, it's helpful to find a linearization of a graph so that you can figure out the acceleration just by finding the slope. So I'm going to make another section of data where I'm going to graph my displacement on the y-axis. This is going to be my displacement in meters, and then my bottom axis, this is going to be my time squared. So that's going to be in seconds squared. Okay, so I need to make another set of data. I need time squared. So 2 squared is 4, 4 squared is 16, 6 squared is 36, 8 squared is 64, 10 squared is 100. So now I need to graph this for my y right here, and this is going to be my x data, okay? So and I need to label my axes. That would probably be helpful. So I'm going to say that this is 0, this is 25, this is 50, this is 75, and this is 100. Okay, and maybe my displacement, I guess I can do it from here. So I would say this is maybe 50, and that's 100, and that's 150. Okay, cool beans. So my first one, right, is, you can't see all my data and my graph with the camera zoomed in, so hopefully you wrote down all of the data. If not, there it is real quick. You can pause. There we go. All right. So my x, I have 4, and my y is 6. So that's about 5 right there. And I think that's 10. Yeah, 10, 20, 30. Yeah, that's 10. So it's going to be about right here. Okay? Doesn't have to be perfect. Just, try to eyeball it. So the next one, I'm going to have 16, so 5, 10, 15, so it's going to be a little close to that one, and 24. So it's going to be just past this line, and then that's 10, 20, 30, so it's going to be about here. And then 36 and 54, okay, so that's 30, 35, 36, and 54, that's about there. And then 64 and 96, so that's 55, 60, 65, and that's pretty close to 100. So it's going to be about right there-ish. And then 100 and 150. Alright, so now you want to make a line of best fit. So it doesn't necessarily have to go through each and every point, but this is probably going to go through every point because I tried really hard to make it accurate. Okay, so that's my line of best fit. So now I want to pick some points that go through some intersections pretty nicely. So I see one that goes through right there nicely. Oh, and there's a good one there. Okay, so I need to find the acceleration. To find the acceleration, I need to do the slope. Okay, so my slope is just y2 minus y1 over x2 minus x1. So my y2, so this is 10, 20, so that's 120, minus my y1, which is about 60, over my x2, so that is 80, minus, and that is 30, 35, 40. Okay, so you just kind of stick that in your calculator, right? I'll probably eyeball it actually, but like 60 over 40, yeah, so 60 over 40, and you get about 1.5, right? Okay, so 1.5, and it's meters, because that's meters is the y-axis, per second squared, and that's your acceleration. Okay, all right, and the reason this works is it's accelerating. So if I want to find the acceleration, instead of going through like this kind of thing, okay, I can if they don't give me instantaneous data, it keeps changing. Instead of calculating at every single point or at the beginning and the end, you do have to make a graph and you have to linearize it. So a straight line is what you're needing. And this one, originally your displacement versus time for this one, it's going to look like that. So when you see a graph with that particular type of arc, your linearization is just going to be to square what you had in the x to begin with. So, and you had t in the x to begin with, which is why we squared that and made that our new x-axis. Okay? All right, and you did this in your summer assignment, so it's not brand new. So, have a lovely afternoon. Bye-bye.